Okay. Please join me in welcoming Joshua Frisch from École Normale Supérieure to talk about the Poisson boundary of linear groups. And I've just started recording, so if you don't want your face online in our thing, turn your camera off.
I should say, if anyone has any questions at any point, please just yell out and interrupt me. I really like getting questions. I can't promise I'll give you a perfect answer, but I will try. And it's, but it's hard to see where they are, in all the Zoom things. So I'm going to be talking today about the Poisson boundary of linear groups, and I will try and bring up the recent work, which I should say is all joint with Anna Erschler at the very end. But really, for the first while, I'm just going to try and give an idea of what the Poisson boundary and what sort of linear functions on harmonic functions on groups really are. And so that'll be the main focus. And then at the end, I will try and cover the new stuff. But the main thing is try and give an idea of the theory, which is very probabilistic, but maybe you don't think about it that way, or maybe you haven't heard of it as something that probabilists could do. So in general, the plan for the talk is first I'm going to define the Poisson boundary. Then I'm going to give examples of, Poisson boundaries. I'm not actually going to ever compute a single non-trivial Poisson boundary, but I will compute enough of it to show something is non-trivial. And I'll focus in particular on the case of Lamplighter groups. If you don't know what Lamplighter groups are, that's fine. I'm going to introduce them. And then finally, I'm going to try and answer our main research question in this project, which was which linear groups admit non-trivial Poisson boundaries. And I should say throughout this talk, groups will be countable, right? Infinite unless otherwise specified, discrete groups, and denoted as G. So whenever I write a G, probably I'm going to be talking about a group. And U is going to represent a probability measure on G. And I'm going to abuse notation a bit. I'm going to write mu of G, which is just going to be the probability I get G. So you can think about this as the integers, and mu might be 50% going left minus 1, 50% going right by 1. And in general, I will not assume, at least in the beginning of the talk, that mu has to be finitely supported, but I will emphasize that somehow finitely supported is often considered, and I would certainly consider the most interesting and most important case for what we're talking about here. And in fact, finitely supported symmetric, moreover, is sort of the most important criterion to think about. So let's start talking about random walks. And I'm sure a lot of you have seen random walks. So I'm going to give sort of the group theoretic point of view on a random walk, which is just going to be generalizing things you've all seen in the Z to Z D setting. So Xn are going to be a sequence of independently identically distributed measures with our distribution mu. And we're going to set y1 to equal to x1, and then yn to be equal to xn yn minus 1. So we're just going to keep on adding symbols to the left, or alternatively, we're going to keep on adding symbols to the right. And a random walk on G with probability measure mu is just going to be the sequence y1, y2, y3, and et cetera, with the product Borel sigma algebra on G to the n. So again, you take a coin flip, you go left, you go right, and then you just keep track of where you are at every time step. And the classical example here is just going to be we do this on the d-dimensional lattice, and the measure is just going to be the uniformly distributed measure, probability measure on the 2D generators of that lattice. Now I want to talk about sort of the weakest notion of asymptoticity that I can for random walks. So this is going to be something that you can think of in some sense as a huge generalization of properties like transience or recurrence or the law of large numbers, or the law of iterated logarithms. It's going to be sort of the most general version of these types of things I can talk about, which is just Dale equivalence. So given two sequences, G1, G2, G3, dot, 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 and H1, H2, H3, H4, dot, 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 we say they're tail equivalent if we can find a pair M and N so that GM is equal to HN, GM plus 1 is equal to HM plus 1, GM plus 2 is equal to HM plus 2, and so on and so forth. So basically, they might be off by, a time shift. They might differ in finitely many spots, but other than that, they look exactly the same. And this is really the sort of, again, anything that I think deserves the name asymptotic should only depend on these pieces of data, right? If I give you two sequences and they disagree in finitely many spots, or they eventually converge to the same thing, eventually they're the same, but they're different, but one, starts maybe a few time steps later, I would totally consider these the same thing asymptotically. And tail equivalence, well, it's well named. It's an equivalence relation. Two sequences which are tail equivalent are asymptotically going to look completely the same. And so a measurable event E is said to be tail invariant if, well, it's a union of tail equivalence classes. Right, so basically this is something where if I tell you, right, of course we're doing probability, we're doing some sort of real dynamics things. So we want measurability, but we're looking just at all events that really only sort of depend on what goes on as time goes to infinity in about the weakest possible sense we can ask. And so, the very basic model of the random walk, which I'm sure you've seen again and again, is, the bettor who bets $1 on a fair coin flip every minute. And we want to just track how much money our bettor has at time end. And so this example, right, when you write it in this random walks language, the group is going to be the integers, and the measure of 1 is going to be equal to the measure of -1 is going to be equal to 1/2. So what are some examples of tail events here? Well, they include, does the bettor hit every number infinitely often? At some point, will they have made $5? At some point, 50, at some point, -7, and so on and so forth. Right, so this is just, of course, recurrence, right? Recurrence is a tail event, right? Because if I just change what happens at the beginning, well, I'm asking whether I hit every number infinitely often. So changing finitely many things, if I remove finitely many hits, I'm still going to hit it infinitely often. Does the path stay above -10 forever past some point? Right, so I guess I should say, right, the random walk is going to be recurrent. And so that's a tail event. It'll happen, probably 1. And will you stay above -10 forever past some point? Well, no, right? You're hitting every point, and therefore you will hit every point, for example, below -10 again and again and again. Now, if instead we took a weighted random walk, right? If instead our bettor was a fortuitous bettor who won, say, 51% of the time, then of course you would eventually stay above -10. So which tail events have probability 0 and probability 1, of course, depends in a very intimate way on the measure. Right? Is, the lim sup of where we stay at time n, we divide that by square root of n, how does this look? Does it stay finite? Well, no. Again, the law of iterated logarithms will imply that it's always going to be infinite with probability 1. And just to give some examples of non-tail events, right? I think when you give examples, you should usually give non-examples as well, is, do I hit 5 in the first 1,000 steps? This is sort of massive, manifestly not an asymptotic event. Does the path always stay above -10? Right, in contrast to the previous one, we're not asking for some point. And the issue here is, of course, having the first few hundred steps, you might dip below -10 and then get above it. So this is not going to be a tail event. And is the sup of yn over square root of n greater than 5? right? Again, the issue is that you might mess this up in the very beginning, which is going to get rid of the tail equivalence. So let me give more examples. And here's a random walk is going to be the free group on 2 generators. And I'm going to, which you should just think about as sort of an infinite 4 regular tree. And I'm going to go on all 4 edges with equal probability. So being transient is a tail event, right? Will I, hitting all group elements only finitely many times? And you actually will be transient here. Having all words eventually begin with A is a tail event. And I think I used a different notation here. I think I might actually prefer my random walks to be right random walks. So I think it might be better if the xn here was multiplying on the right. Annotates that. So it's the same basic idea, right? Up to a flip, it's exactly the same. Get rid of this. And having all words eventually begin with A is a tail event. But having all words begin with A is not a tail event, right? Maybe your random walk first, started at the identity, then went to B, then went to B squared. And then after a bit, it ended up going to A, but it took it a little bit of time. Any questions so far? Okay. So I just want to note that there's a natural group action on the space of sample paths, right? We have all these sample paths, right? And if I have H1, H2, H3, H4, if that's my trajectory, I can just do GH1, GH2, GH3, GH4. And this is also going to be a trajectory. So, right, so this is just the trajectory you get if you start your random walk at G and do the same increments, but start at a different point. And the translation action is going to send tail equivalence classes to tail equivalence classes. And thus it's going to send tail measurable events to tail measurable events. So what is the Poisson boundary? Well, it's basically everything I just told you so far. Right? It's a Poisson boundary of a group, G. If I give you a group and a measure mu, I look at the quadruple of all infinite trajectories, the sigma algebra of all tail invariant events, and then the random walk sample path measure mu, and the diagonal action of G on itself. And this action turns out to be stationary. You don't need to know what the word stationary is here. I'm just including it for those who do know. Okay. So now we have this definition, and the point is the Poisson boundary is supposed to represent all the sort of possible asymptotic events one might see. Right? It captures the space of asymptotic events, and that's all very good. But in some sense, why do we care? Right? We've just made some elaborate definition, and I will cover this soon. But I want to cover a few properties of the Poisson boundary first. So first of all, again, the action of G on the Poisson boundary is stationary, which just means if I apply a random element, random chosen with respect to mu, well, and this is horrible notation on my part, but on average, you're not going to, right, the average measure of a set is not going to change from this. Right, and given any event E of measure less than 1 and greater than 0, there exists a G right? Such that I can send any event with any non-full measure to the measure less than epsilon. So basically, even if I start with something that's very, very likely, I can find some group element where it's not so likely. The Poisson boundary is non-trivial if and only if there exists a G such that the random walk starting at G has a different scale distribution than a random walk starting at the identity. And G mu is a non-trivial Poisson boundary if and only if there exists a constancy and an H in G, so that the total variation distance between H of Yn and Ym is bounded below by some constant.
I have a question on what it means to be non-trivial for a Poisson boundary, given that it was a quadruple of things.
Good question. So the Poisson boundary, in addition to all these complicated things, it's a measure space. So we say it's trivial if and only if it's trivial as a measure space. So all sets either have measure 0 or measure 1. Right, and that will actually automatically sort of fix everything else. Right, we're viewing this as a measurable object, so we really are not going to care about null sets. And well, if you have like 0, 1 measure space, that means the group action is just going to send measure 1 sets to measure 1 sets, measure 0 sets to measure 0 sets. There's nothing sort of going on. There's no there.
Okay, thank you.
Yeah. Right. So now I'm gonna switch gears a little bit and talk about harmonic functions. So given a group G and measure mu, a function from a group to the reals is harmonic if f of x is just the average when I take one step with respect to mu. And I should say, of course, the above sum is not well defined in total generality, but of course, if your measure, for example, was finally supported, or more relevantly for us, if we're talking about bounded functions, the sum will always exist. And f is a bounded harmonic function if it's both bounded and harmonic. And I should say there's also a natural G action on the space of harmonic functions, right, where you send G of f of x to f of G inverse of x. And the G inverse might look weird at first, but it's actually just what you get when you when you actually write down the formulas and look it out. And the foundational sort of thing, the reason we really care about the Poisson boundary is because of the following correspondence, which is due to Furstenberg. Right? I should say it's called the Poisson boundary because Furstenberg called it the Poisson boundary. But of course, right, Poisson was hundreds of years before. He was not thinking about abstract group actions on measure spaces. It really is almost entirely due to Furstenberg. Some predecessor ideas were, I think, independently discovered by Blackwell, and some ideas were, I guess, contemporaneously or maybe a little later discovered by Margulis. Right? So the key theorem is the following, right? Well, the Poisson boundary, it's a measure space with a group action on it. And the bounded harmonic functions, these are this vector space of functions. And well, a priori, these look like completely different things. But it turns out that if I look at the space of all L infinity functions on the Poisson boundary, again, the Poisson boundary here, we're just thinking of it as a measure space. And so I just take some almost everywhere bounded function. Then there's going to be a harmonic function, which is bounded and harmonic corresponding to it. And vice versa, if I have a bounded and harmonic function, I will have some non-trivial, right? That'll give me some L infinity function on the Poisson boundary. So I should say the facts that these things are going to be isomorphisms. The way I think about it is you're just going to wave your hand and say martingale convergence a few times. The proof of this, once you sort of have all the machinery up, it's not completely trivial, but it's not very difficult. But I want to at least explain a little bit how this isomorphism works, which is that you take an indicator function on a tail event E. So I give you some tail event E, and I look at the indicator function on that. So it's 1 at that event E and 0 everywhere else. And what I do is I ask for the probability that if I start a random walk at G, I end up in this tail event E. So this is, it's pretty easy to immediately check that this is harmonic, right? Because the odds that starting at G, I end up in some tail event, well, it's just going to be harmonicity just says I'm the average after one step. And of course, the probability that I end up there is exactly the average of the probabilities after I've taken one step. Any more questions so far? All right, so I've talked about this measure space. So I guess I should actually, I want to bring up, before I really do this, I want to bring up one really important thing. So this is a correspondence, right? You have a group action on both these things. You have a vector space on both these things. But maybe the easiest way to see that this is interesting is because, well, what does it mean if your Poisson boundary is trivial? What does it mean if you have only, if all your bounded harmonic functions are constant? It turns out these are the same things. So having a non-trivial harmonic function, a non-constant harmonic bounded harmonic function, will give you a non-trivial Poisson boundary, and vice versa, having a non-trivial Poisson boundary will give you a non-constant bounded harmonic function. And these, a priori, at least to me, look like completely different things. So let me, try and focus a little bit on this case of F2. So again, the group is going to be F2, and we're going to have mu of A is equal to mu of A inverse is equal to mu of B is equal to mu of B inverse. And the non-trivial event is, do all but finitely many elements start with A? This is part of why I brought this one up earlier. So I just want to analyze this, and I want to show that this event is non-trivial. I want to argue that it's going to happen 1/4 of the time. Well, first of all, right, look at the time. Let WT be the length of the word at the time t. So this is just, how far away you are from the origin. Well, then, 3/4 of the time, I'm going to move one step away. And 1/4 of the time, I'm going to move one step closer. So on average, I'm going to move half a step away. And I'm lying a tiny bit because, of course, if you're exactly at the origin, you will, always move one away. But in fact, that'll only happen finitely many times because you're transient, so it's not going to affect things. Right, so 3/4 of the time, you're going to add a letter. 1/4 of the time, you're going to remove a letter. Right, so looking at the coupled random walk and applying the strong law of large numbers, what that means is that eventually, your length is going to be above 0 and never return to 0. Right, so this is big, right? So you will eventually, at some point, just have your word grow longer and longer and longer and longer. And thus, but if you think about this, right, when your word is going longer and longer and longer and longer, this just means I'm, messing up things at the very end. If I want to change the first letter, that can only happen when I'm of length 0. And thus, eventually, my first letter will be fixed. It might be A, it might be A inverse, it might be B, it might be B inverse. But by symmetry, it's equally likely to be any of the four. And so I just want to give a light picture here, which so here's my free group, right? And we start at the origin right here in the center. Give me a second. Right, so we're going to start right here, and then our random walk, right, it's going to do something like this. It might go here, and then 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 here. But if you can sort of imagine it, right, it's very, very unlikely to just undo everything that it did. On average, you're going to just get one step further in the tree, or not one step, half a step further in the tree. So you're very unlikely to return here again and again and again. And of course, if I leave this thing, I can't switch which of the quarters I'm in, except by returning. So once I've left, this, point for the very last time, I'm going to be stuck in that quarter forever. And then by symmetry, you're equally likely to be in all four parts. All right, so that's the example of, I want to say, when things are interesting and non-trivial, and when this Poisson boundary is a non-trivial object. So let me just try and talk a lot about some results here. So first of all, let me ask a very basic question, which is which groups have trivial Poisson boundary for all measures, right? I keep on talking about this as, something with a group and a measure, and of course it is, but wouldn't it be nice if it was sort of purely a group theoretic property? Blackwell showed that for z to the d, you always have a trivial Poisson boundary. So what that means is that for z to the d, there's every asymptotic event will either always happen or never happen. And this is an incredibly strong statement. I don't think it's a priori at all obvious, right? So it's, of course, well known that transience and recurrence, some happen probably 0, the other happens probably 1. The law of large numbers will happen with probability, 1. But it's the same, that's sort of any asymptotic thing you can ask about. It'll either always happen or never happen. Equivalently, if I have any bounded harmonic function, it's automatically constant. So this is, the discrete analog of the Liouville theorem from complex analysis. Choquet and Denis generalizes to all abelian groups. And then Dink and Maljutov generalizes further to nilpotent groups. And nilpotent groups are basically those groups which grow polynomially. Right, so these are, functionally just symmetric graphs with, right, these are the groups which grow exactly polynomially. And Furstenberg showed that non-amenable groups never have trivial Poisson boundary, sort of regardless of what measure you choose, under the very mild non-degeneracy condition that, your measure generates the group, or the support of your measure generates a group. And Kaimanovich and Vershik showed that all amenable groups have trivial Poisson boundary for some measure. And then I, in joint work with your Hartman, Omer Tmud, and Puya Vihidi Verdowski, showed that if you're non a virtually nilpotent group, so if you don't satisfy this thinking Maljutov criterion, then you have a measure with non-trivial Poisson boundary. So there's sort of a thing here. So we really do have a good understanding of this question if we look at the class of all measures by this point. We know when you always have a trivial boundary, we know when you sometimes have a trivial boundary, and we know when you never have a trivial boundary. And I should say, for people who are not group theorists, non-amenability is sort of a strengthening, a quite powerful strengthening of having exponential growth And one thing which implies it's not equivalent, but somehow for any group you're likely to see if you're not a group theorist, it probably is equivalent to, it's implied by having a non-trivial free subgroup. It's not equivalent, but in many classes of groups, there actually is an equivalency here. And so now I want to just sort of focus specifically on Lamplighter groups, which I think are a good, demonstration of the power of the theory. And these Lamplighter groups, I'm about to define them. I should say, it's in this previous mentioned thing, Kamenovich and Vershik, in this paper, they were the first ones to consider these. And these really, even to this day, are somehow the basic examples which show up in the theory. So you can write these as reef products. So it's going to be the semi-direct product of z mod 2z to the z to the d with z to the d with homomorphism given by shifting. But nobody thinks about it this way, right? Well, I guess some group theorists do. But the way we all think about it is much more visual, much more, I want to say, pictorial way, which is you just imagine, let's let d equal 2 for right now. We imagine our walker just walking on two-dimensional space, turning on and turning off lamps, right? So basically, we're in a two-dimensional plane of lamps. Let me see if I can draw a little picture here. Well, it's not going to be. I'm not such a great artist, but we have a bunch of lamps here, and we have a walker. And the walker is just going to go left and right, forwards and backwards, and at every step, he can either turn on or turn off the lamp. Right? So the lamp can either be right. So basically, what the group is that you just tell me the steps as a walker, and at each step, whether he switched the lamp or whether he kept it the same. So maybe my walker will go left, then right, then left, then turn on a lamp, then go right, then left, then turn off a lamp. Maybe he'll do something different. And this generates a group, and it's called, because of this evocative image, the Lamplighter group. And I should say, these groups are actually solvable groups. And in particular, they are amenable groups. And, you get a different one of these groups for every d. So let me talk about the three-dimensional one. So now our Lamplighter is a bird, flying up, flying down, flying left, flying right, flying in all directions. And what we're going to do is, our Lamplighter is going to go in each of the 6 cardinal directions, with equal probability, and also with some probability, the Lamplighter will just take a break and flip the lamp. So if it's off, they'll turn it on, and if it's on, they'll turn it off. So the point is that this has a non-trivial Poisson boundary. So this is, some complicated group. It's not such a complicated measure. It's not at all obvious how you would construct a harmonic function on this thing, right? It's how in the world am I going to construct this complicated bounded harmonic function on this thing? But the Poisson boundary is non-trivial. And here's why. Well, let's just look at the lamp at the origin. Well, our bird's flying around, turning on, turning off lamps. But if we just look at where our bird is at z cubed, on z cubed, right? They're just doing a regular random walk on z cubed. They're going in each of the 6 cardinal directions with some probability. But on z cubed, random walks are transient. And thus, eventually our bird, eventually a random walker is going to return to the origin for the very last time. And so if I say, I've returned to the origin for the very last time, I've turned the lamp on or I've turned and the lamp was on or the lamp was off, well, it's going to stay on or off, the lamp at the origin, for the rest of all time. And because of that, well, with probability 1, right, whether the lamp is left on or left off, these are going to be non-trivial events, right? Each of them will happen, the lamp at the origin, each will happen with some positive probability, but with probability 1 of the two will happen. So this gives you a non-trivial bounded harmonic function. And if anyone wants to challenge that, I would suggest trying to sit down and draw or compute a harmonic function on this thing any other way. It's really not clear, other than this thing, why these harmonic functions should exist. And I should say, this argument fails to work in 2 dimensions, right? Because in 2 dimensions, you're recurrent. And actually, this isn't just some subtle technicality. This isn't just a sign that, well, we need a different argument. But the boundary is actually trivial in 2 dimensions. So if I have a 2-dimensional lamplighter who's going around, walking left, walking right, doing all these things, there are no non-trivial tail events here. And I don't quite have time to do the proof. I will say all it basically relies on is this fact, due to Choquet-Denis, that is true for abelian groups. From there, the argument is, very quick. And it shows that there's real subtlety to this question of whether the boundary is trivial or not, right? Because these 2-dimensional and 3-dimensional lamplighter groups, I don't think anyone would have ever a priori guessed, yes, these should have different boundary behavior. Any questions so far? All right. So with my next bit of time, I'm going to try and talk a little bit about what's going on for linear groups. So a linear group is just going to be a group of matrices over some field F. And by Tit's alternative, any countable linear group is either non-amenable, which, as I mentioned earlier, always has a non-trivial Poisson boundary, or solvable. And actually, it's even better than that, right? If you're solvable, then you have a finite index subgroup, which, or at least if you're finally generating solvable, you have a finite index subgroup, which is actually, honest to goodness, upper triangular. And somehow, finite index is not going to affect most of what we do in this theory. We're not going to talk about any, so I'm going to focus on these upper triangular groups. Suffice it to say, of course, anything will go over because it's more general thing. Right, so basically, in order to study linear groups, all we have to do is study upper triangular groups. So groups consisting entirely of upper triangular matrices. But I should say, this is not immediately so obvious, right? Upper triangular groups are pretty complicated. And in particular, right, these lamplighter groups, which I just mentioned, these are even examples of 2 upper triangular groups where the matrices are 2x2 matrices. And we're going to focus here on finitely supported symmetric measures. The notion of finite support can be weakened substantially, right? So in particular, we can weaken it to a finite second moment condition, which is just saying on average on sort of the group, on the Cayley graph of the group, I move at most a finite distance, and I have a finite second moment of the distance I move. So the main theorem, which I'll try and explain at least a little bit on the next slides, is somewhat more technical. So let me try and start with a corollary, which I think captures the flavor of the result pretty well. So let F be a field of positive characteristic with transcendence degree at most 2, or a field of characteristic 0 with transcendence degree at most 1. Then a matrix group G over F either is non-amenable, so it's either this case where you always have a non-trivial boundary, or has a Liouville property. And the Liouville property, I probably should have given the explicit definition earlier here, but it's just your Poisson boundary being trivial. So for finitely supported symmetric measures. So either you belong to this very general class where you're always non-trivial, or you belong to the special class where for every finitely supported symmetric measure, you're trivial. And so I want to talk for the next little bit about a special class of groups for which are already somehow going to capture most of the interesting phenomena. And I will give some, explanation for the next bit about exactly how they capture this phenomena. So, a basic block is going to be a group generated by delta, and finally many mxmy of the following form. So we're going to have this delta matrix, which is just 0, 1, 1, 1 thing. So this is just going to be an upper triangular matrix, which is 1 on the upper diagonal. And we're going to have these mxi, yi's, which are just going to be xi on the upper left and yi on the bottom right. So basically, we're going to have a bunch of diagonal matrices in the single 1, 1, 1, sort of the most trivial example of an upper triangular matrix that's not diagonal you can get. And the question, is somehow going to be, when are these trivial and when are these non-trivial? When does these groups have a trivial boundary? When does these groups have non-trivial boundary? But before I do that, I want to emphasize, bring up sort of why I'm really doing it. And the point is going to be, you can really reduce the n by n case to this 2 by 2 case. So n by n matrix groups, like upper triangular groups, are actually pretty complicated. If you start trying to understand what they look like, you pretty quickly get into some technical weeds. 2 by 2 matrices are somehow much more reasonable to compute with. They're much simpler. They're much more concrete objects to actually touch. These n by n ones are pretty complicated. So our first thing is we're going to try and figure out a way to get from n by n matrices to 2 by 2 matrices. And again, I apologize for the technicality, but this is sort of the way the mathematics actually looks. So we have, our diagonal. So I want to look at all the elements which are diagonal and 1 on the diagonal. Sorry, so all the upper triangular elements which are 1 on the diagonal. And then I want to look at the places above the diagonal where they're non-zero, right? And I want to call some of these places good. So if I look at this point ij here, I have this 1, 1, 1, 1, 1 thing, and then I have a bunch of zeros. So if I just restrict sort of to this square between I and j, well, I have 1 on the diagonal, but everything above this star is going to be 0. So we say a position is just going to be good if, ij is good, if you have some all ones matrix on the diagonal that looks like this. If you have something where the ij coordinate is non-zero, the diagonal is all ones, your upper triangular, and everything above ij either to the left or below, or to the left and below, but not on the diagonal, is all zeros. And so assuming I have one of these good elements, I want to associate a basic block. And the basic block is just going to be, I have 0, 1, 1, 1, and I take all the possible MII and MJJ I can possibly get. So really, having this, sort of element which is 0 in a lot of places but not on the ij coordinate, it's going to be a form of non-degeneracy condition. Somehow, if you look at a lot of natural groups, you will automatically have this show up. And so then, right, the ij block is valid if you have elements, which sort of look like the left, and then we want to look at the block. And so the first main theorem we show is a reduction theorem. And this is, Anna and me. So let G be a group of upper triangular m by m matrices over a field, and let mu be a finite entropy non-degenerate measure. The Poisson boundary of G mu is non-trivial if and only if I can find some basic block where it's non-trivial. Now, of course, the Poisson boundary depends on both the group and the measure. So what do I mean that it's trivial on the basic block? Well, the point is I can actually take any measure I want on the basic block, so long as its projection to the II in JJ coordinates, so long as sort of the two diagonal coordinates have the same measure on both things. So really, this is going to be a way to take our finitely supported measures on m by n groups and reduce them in a very concrete way. It's a little complicated sounding, but when you actually try and apply it to some groups, it's very concrete, and get 2x2 matrices. And you're non-trivial if and only if one of these basic blocks already has a non-trivial boundary. And I should say, I think neither direction of this is obvious. It's not actually obvious that if one of these 2x2 things is non-trivial, why you automatically have a non-trivial boundary. And the other direction, that if these are all trivial, why you have a trivial boundary is also not obvious. Right, so this, again, the exact statement is, I understand, a little technical, but the key point, the key takeaway is that you can really reduce this question about a priori very complicated m by n matrices to 2x2 matrices. All right, so now we've reduced everything to the case of 2x2 matrices. And well, 2x2 matrices are, and actually even better, we've reduced it to these basic blocks, which are very simple 2x2 groups of 2x2 matrices. They still can have fairly complicated behavior, but they're at least they're sort of a very special form, right? And I should say the results here are only going to work for nice enough measures, which means they have to be close to finitely supported. Again, finite second moment will generally do here, and they have to be symmetric. Symmetricity is sort of a vital assumption here, even for the one-dimensional Lamplighter group, right? Even for these groups which I mentioned earlier, which have trivial boundary, if you lose symmetricity or some sort of weakening of symmetricity, pretty quickly boundaries have a tendency to be non-trivial, right? So let's say we have a basic block. So this is this very special form of 2x2 matrices. And let FB be the minimal field, which includes all these values, xn divided by yn. Right, so I have this xi and yi, and then I look at the quotient. And then I look at all these quotients. There's going to be some field, some minimal field, which includes all these quotients. Well, if mu is finitely supported and symmetric, and the transcendence degree of this field is less than or equal to 1, the boundary is trivial. If mu is finitely supported, or even more generally, finite entropy, here we don't need any symmetricity assumptions, and the transcendence degree is at least 3, the boundary is non-trivial. And in characteristic 2, well, in the positive characteristic case, you're also trivial, but in the characteristic 0 case, it's very subtle what goes on. Sometimes you're trivial, sometimes you're non-trivial. We have sort of a guess, conjecture as to what goes on in general. But the exact phenomena is fairly nuanced and doesn't just depend on what field you belong to. So this gives a complete characterization this and the previous theorem for m by m matrices over positive characteristic fields. And for characteristic zero fields, it gives a lot of data, right? Usually, or very frequently, you'll see, a block of dimension 3, or notice that all the blocks are dimension at most 1. But for these 2 by 2 blocks, there's still some work to be done. And yeah, I think that's